Hi class. In this brief tutorial, we're going to discuss Rene Descartes' rule of signs, right? And the usage of it. So the rule Descartes' rule of signs is used to give us an understanding or an idea of how many positive zeros that may exist, how many negative zeros that may exist. Additionally, it will also provide us with the how many complex numbers may exist in a given function. All right, to apply Descartes' rule of sign, we use the original f of x and we examine the amount of changes, the signs change when going from one term to the other. Now, this is obviously works. It is obviously advisable that you put the the actual polynomial in standard form. You want to be able to put it in standard form when you determine the amount of sign changes. But to begin doing it, you take a look at the original function, and then once we've done counting how many sign changes in the original f of x, we do the same for f of negative x, right? And we will evaluate the function when x is negative. So first, we take a look at the original function, and I'm going to use a red pen to show changes. Now, so the leading coefficient of 5 has a positive sign, and then it moves over to -3. So there is a sign change that occurred here, and followed by another sign change when it went from -3 to +2. Now, it's moving to another positive, and then another sign change here. So if I were to document now the amount of sign changes, and I'm going to put that into this. So when we work with f of x, the original, that'll tell us how many positive zeros that may be existing in the function. When we evaluate f of negative x, that'll give us how many negative zeros exist or may exist. And then since the degree in this example is 5, it's a degree of 5 polynomial, there can be no more than a total of 5. So all of it should add up to 5. But we must also include complex, which is a combination of real and imaginary zeros. Okay, so these three will be looked at, but using the Descartes rule of signs, that will tell us what the positive and the negative zeros are, and then we can just use basic calculations to figure out how many complex there should be. So for the first one, we've already found out that there can be 3 positive zeros. But the theorem also, to clarify it a little better, it's not just 3. It's possible that it can be 3, right? Or is less than the number of sign changes by an even number. So say the next even number would be 2, right? So if you do 3 minus 2, which would be 1. So it's either 3 and 1 are the possible positive zeros. So it can either be 3 or 1. Now looking at the negative. So we're going to take f of negative x. So let's use, and I'm going to come up here and evaluate negative x. So that'll be, and then you'll just substitute the x with the negative x's all the way through the problem. Right, so if you take a negative variable to an odd power, it'll remain negative. So x to the third, negative x to the third will remain negative x to the third. So I'll bring that negative to the front of the coefficient, leaving it negative 5x to the third, right? And then you'll move on. And then a negative variable to an even power will make it positive always. So now this would become negative x to the fourth, which is positive x to the fourth. That'll make it negative in the positive, which is negative x to the fourth. And I'm going to continue all the way through and get all of them done. This becomes negative 2x to the third. That becomes plus x squared plus 2x minus 5. All right, and now we're going to evaluate what we've already evaluated. We're going to look to see the sign change. So from the first, and this number doesn't look clear. That's supposed to be a 5. It looks like it's a 3. I'm just going to make sure I clarify it. This is a 5. Okay. So now we all know that's a 5. All right. So there are no sign changes from -5 to -3, neither from -3 to -2. But there is one here. So here's a sign change. And then the next one is here. So there are 2 sign changes that occur. So it can be either 2 or the next even integer less than 2 would be 0. So it can either be 2 or 0. Okay? So now I'm going to run these down to fill this table in so that we can get an idea of the positive, negative, complex, and then total zeros. All right? So now if there are 3 positive zeros and there are 2 negatives, then that'll be 5. Therefore, you cannot exceed 5 because it's a 5th degree. So therefore, there will be no complex zeros, giving it also a total of 5 zeros altogether, or 5 roots, right? Whether it be imaginary or real. But since both of them, one is positive, one is negative, then there are 5 real roots. 3 are positive, 2 are negative, and none are complex, right? Now, if there is no negative zero, so we're going to do now run it 3. I'm going to run this table with 3 again, 3 positives, but now no negatives. So therefore now we are lacking in real zeros. Then the rest, the other 2, would be complex zeros. That will total into 5. So all your total should be the total of the degree. All right, now that I covered and completely done the 3s, now we'll look at one positive zero. If there is 1 positive zero and 2 negative zeros, that'll be a total of 3. Then there will be 2 complex, giving it 5. 5 total. Once again, if there is 1 positive zero and no negative zeros, then the rest are going to be complex zeros. So that'll be 4 complex. That also gives it a total of 5. All right. So this is us analyzing now the, possible scenarios that may exist in this given function. And this is laid out all together. And this is how we answer the question using this is how we discuss real zeros using Descartes' rule of signs.